In this video, we're going to continue looking at GL2, which is the set of 2 by 2 matrices that have determinant equal to something other than 0. The determinant, of course, of a 2 by 2 matrix is given by this formula. It's very easy. You simply multiply the elements on the main diagonal and you subtract off the product of the elements on the off diagonal. It's worth noting that determinants of larger sized matrices are not that easy. We've also looked at the definition of matrix multiplication as it applies to 2 by 2 matrices. To quickly go back over this matrix, this 1, 1 entry is formed by dotting the first row of the first matrix with the first column of the second matrix. The 1, 2 entry of the product matrix is formed by dotting the first row of the first matrix and column 2 of the second matrix. The 2, 1 entry of the product matrix is formed by dotting row 2 of the first matrix with column 1 of the second matrix. And the 2, 2 entry of the product matrix is formed by dotting the second row of the first matrix with the second column of the second matrix. In the first video in the series, I made the claim that GL2 under this multiplication is indeed a group and in fact a non-commutative group. In the previous videos, we have shown that GL2 under its multiplication is closed and associative. And in this particular video, what I want to do is I want to finish off the problem of showing that GL2 under its times is a group. In other words, we need to show that GL2 under its multiplication has a right identity element, and we need to show that every element of GL2 has a right inverse. And finally, we need to show that times is not commutative. To get started, let's go looking for a right identity element. I am going to let I be the matrix 1, 0, 0, 1. And you may remember from linear algebra that this is a multiplicative identity, but we are going to prove what we need to in this video. The first thing that I want to do is I want to make a note that I does belong to GL2 since the determinant of this matrix is 1 minus 0, which is 1, which is not 0. Next, if I let A be a matrix that is inside GL2, we have the following matrix product. If I look at A times I, you will notice that I have put I on the right side of the product. This is, of course, A, B, C, D times 1, 0, 0, 1. And when we use our matrix multiplication definition, this is going to be A times 1 plus B times 0, and then we will have A times 0 plus B times 1, and we will have C times 1 plus D times 0. And the final element will be C times 0 plus D times 1. And when we clean up the arithmetic, this is indeed A, B, C, D. So I is a right side identity. We do not need to worry about whether or not it works on the left side in order to claim that GL2 is a group. So we're not going to worry about doing that one. We will move on to right inverses. Now for right inverse elements, what I have to do is I have to let A be any element inside GL2. Now I do want to make a note that says that the determinant of A, which is AD minus BC, is not 0. I need to find a B inside GL2 such that A times B is equal to the right identity that we just got done dealing with. Again, you will notice that the B is on the right side of the multiply. I do not need to worry about whether or not BA is the identity because all I need is a right inverse. Well, I'm going to actually simply make a choice here. I am going to let B be the following matrix. We're going to have D divided by the determinant of A. And for this entry, we're going to have minus B divided by the determinant of A. And down here, we're determinant of A. And over here, we're going to have A divided by the determinant of capital A. And this is indeed where A is the matrix A, B, C, D. So these A, B, C's, and D's are the same as they are in A. And remember, the determinant of A is known not to be 0 since A belongs to GL2. So that means I can divide by it. Well, I have to show that B is a right inverse for A. That means I have to show that B belongs to GL2 and that that A times B is indeed equal to I. So I kind of want to make those notes. So we need to show, first of all, that B is indeed part of my set GL2. And second of all, I need to show that A times B is indeed equal to the right identity. So let's look at each one of these questions separately. So is B in GL2? I've already got the calculations written out because there's a lot of symbol crunching that needs to be done. I'd like you to listen to the video and watch what I'm talking about rather than trying to frantically take notes. And then if you want to get this all down in your notes, rewatch the video, stopping between every step and copying the algebraic manipulation down. So to figure out if B is inside GL2, the first thing that we do is we have to take the determinant of B. And the determinant of B is the determinant of this matrix. And of course, what that means is we need to multiply these two elements on the main diagonal and subtract off the product of the off diagonal. Now, when we do that, this is what we get. And what I now need to do is I simply need to clean up the arithmetic here. When I clean up the arithmetic, we're going to get this expression here. We get AD over the determinant of A quantity squared from this particular stuff. And over here, I've got to keep track of minus signs. We have a minus times a minus, which is plus, times another minus, which is a minus. And that's where this minus sign comes from. And then we have BC over the determinant of A quantity squared again. Now, when we've got two fractions that have the same denominator, it's very easy to add them or subtract them. We can just put the numerators with the appropriate things. So this expression here is the same as this expression. Now, I do need to remind myself that the determinant of A was the determinant of A, B, C, D. And so the determinant of A is just AD minus BC. So what we're looking at here is the determinant of A divided by the determinant of A squared. In other words, we wind up getting this piece of arithmetic. This expression becomes this, which becomes 1 over the determinant of A. And since the determinant of A is not 0, its reciprocal is also not 0. And this says that my matrix B is indeed inside GL2. So it's possible for B to be a valid right inverse element. We still have to check out if A times B is equal to the identity. So let's check that out. So is B a right inverse for A? Again, I have all of the arithmetic algebra stuff written down, so watch what I'm saying about the argument without worrying too much about trying to copy everything down, and then go back and rewatch the video and stop the video after each algebraic step so that you can get a clean copy of it in your notes. To figure out whether or not b is a right inverse, I have to multiply them. And a times b is given by this expression here, because this is a and this ugly thing is b. And I know how to multiply that, so we're going to multiply that. When we multiply that out, this is the matrix that we get. And just to double check, we're looking at that particular row times this column to get this entry. We're doing this row dotted with that column to get this entry. We're doing this row dotted with this column to get this entry. And we're doing this row dotted with this column to get this entry. And so once we double check all of the arithmetic there, we can start thinking about how are we going to simplify this. Well, it simplifies in this particular fashion. Here, I've got two fractions that are over the determinant of a. So that's just going to be the tops over the common bottom. In other words, this entry here becomes AD minus BC over the determinant of a. If I look at this, I've got minus AB and I've got a plus AB, both over the determinant of a. That's where that 0 comes from. Likewise, these two terms are the same except for that minus sign, and that's where that 0 comes from. And if I clean up this and put this term first, I'm going to have something that boils down to AD minus BC over the determinant of a. And what I want to do is I want to remember that the determinant of a is the determinant of A, B, C, D. And so that is AD minus BC. And this fact here is how come this entry and this entry both become 1. But what we now have is A times B is indeed equal to the multiplicative identity for this particular structure. So B is a right inverse for A, and it is inside GL2. Let's remind ourselves that B is indeed inside GL2. And that means that GL2 satisfies axiom 4, and hence GL2 under its times satisfies all 4 axioms, and this thing is indeed a group. Now, the very final thing that we have to do is show that this group is not commutative, and that's super easy. So let's let A be the matrix 1, 2, 3, 4, and let's make B the matrix 1, 3, 2, 1. It's important to note that A is inside GL2 since the determinant of A is 4 minus 6, which is minus 2, which is certainly not 0. And also B is inside GL2 since the determinant of B is 1 minus 6. And that's minus 5, and minus 5 is certainly not equal to 0. And now all I want to do is I want to compute the two products. A times B is going to be 1, 2, 3, 4 times 1, 3, 2, 1. And when we compute this product, we're going to get 1 plus 4. And here we're going to get 3 plus 2. And in this entry, we're going to get 3 plus 8. And in this entry, we're going to get 9 plus 4. So this matrix looks like it is 5, 5, 11, 13. And let me clean up my notation there because that's a little bit ambiguous. So there. And if I turn the two matrices around, we're going to have 1, 3, 2, 1 times 1, 2, 3, 4. And when we compute this product, we're going to have 1 plus 9 and 2 plus 12. And we will have 2 plus 3, and we will have 4 plus 4. And when we finish the arithmetic, we get 10, 14, 5, and 8. And these two matrices are clearly not equal. So the result is AB and BA are not the same thing. So our group GL2 under its multiplication is not commutative. And so we have an example of a non-commutative group. And this particular example is a very important example. By the end of the course, we will have lots of non-commutative groups.